Hey everybody, welcome back. This week we're going to be learning about the independent samples t-test. There's some things that I want you to be able to do by the time we get to the end of this unit. I'd like you to be able to determine when to use the independent samples t-test to analyze data. I want you to be able to write the research and null hypotheses in symbols and words to fit the research question. I want you to be able to determine whether you can run an independent samples t-test through checking the assumptions and determining if it's robust to any violation of those assumptions. I want you to be able to calculate and explain the meaning of the independent samples t-test. I want you to find the correct critical values for the independent samples t-test based on the research question, alpha level, and data set. I want you to be able to write and interpret the results for the independent samples t-test. I want you to be able to calculate and interpret the relevant follow-up analyses for the independent samples t-test. And then finally, I'd like you to use the hypothesis testing steps to run an independent samples t-test to analyze a data set. All right, so let's get started. Our first step, remember, we're following those hypothesis testing steps every week, and the steps don't change. We have step one, where we're going to determine our statistical analysis that we're going to use. What are our other steps? Pause me right now and try to practice that. So step one is determine which analysis you're going to use. Pause me. Okay, so step one, we figured out. Step two, we're going to write our research and null hypotheses and symbols and words. Step three, we're going to check our assumptions to make sure we can run the analysis. Step four, we're going to calculate our test statistic. Step five, we're going to find our critical values. Step six, we're going to make a decision. And step seven, we're going to conduct any relevant follow-up analyses. So we're going to follow that same process over and over again. It's going to start feeling like Groundhog Day out there. But the process is the same. We're just using different statistical analyses that we're taking through the same process. So we remember from the last couple units that there are certain questions that we ask to determine what statistical analysis we're going to use. One of those is, what's the purpose? So this week we're learning the independent samples t-test. So what's the purpose of this analysis? It's to find significant differences between groups. Another question that we ask is, how many samples does it test? And the independent samples t-test is going to test the difference between two samples. Another way to say this is that our independent variable has two levels to it. And we remember previously that IV is our symbol for independent variable, and lowercase italicized k is our symbol for levels of the independent variable. In other words, how many groups are there? Three, what type of basic research design does the independent samples t-test use? This one uses a between group design. What level of measurement is the dependent variable? This is a common one. And here that's going to be a scale. Remembering that scale means that we're our dependent variables on an interval or ratio level of measurement. All right, so if we sum it all up, we use the independent samples t-test to see if there's a significant difference between two groups made up of different participants with a dependent variable that's on an interval or ratio level of measurement. Again, we use the independent samples t-test to see if there's a significant difference between two groups made up of different participants with a scale dependent variable. So on your statistical analysis sheet that you've been building, you will want to write the independent samples t-test in there along with the one sample z-test and the one sample t-test. Each week, you're going to want to keep making sure that you understand which analysis does what things, because that's something that I really want you to be able to get out of this class. So then we move on to our second step, which is to write the research and null hypotheses. First, we always got to decide whether we're going to write our hypotheses directionally or non-directionally. We only choose to write our hypotheses one way. Even though I'm sharing with you how to do these different ways to write hypotheses, when writing them for whichever research question that you're asking, you're going to choose either to write them directionally or non-directionally. What were some of the tips that we learned for writing hypotheses? Think about those and say them out loud before we move on. Some of the tips were to write our hypotheses out in symbols first. Another one is to write our research hypothesis first and then write our null hypothesis. Another tip was to keep our groups in the same order, so that it makes it easier to write our null hypothesis after we write the research hypothesis. All right, so non-directional hypotheses. So if we're looking at the independent samples t-test non-directionally, with our research hypothesis and symbols, the first thing that we're going to do is we're going to write our symbol for research hypothesis, which is H sub 1. And then we're going to put a colon after it to let us know that our research hypothesis is coming. We remember from a couple slides ago that we're using the independent samples t-test to see if there's significant differences between two groups. Specifically with the independent samples t-test, we're testing to see if there's a significant difference between the means of each group. So when we're writing our research hypothesis, we'll have our H sub 1, our colon to say that our research hypothesis is coming. Then we'll put X bar sub 1, which represents the mean of group 1. Then we'll put the not equal to symbol, because when we write non-directional research hypotheses, we don't have an idea of which group we think will be bigger or which group will be less or lesser. And then after that, we'll write the symbol for the mean of group 2, which is X bar sub 2. And then you can see at the bottom of the slide that H sub 1 colon X bar sub 1 does not equal X bar sub 2 is how we would write a research hypothesis in symbols for an independent samples t-test. So we can also translate those symbols into words. And so here I have a template for you. This means that you would take the characteristics of whatever study that you're doing and put it into this template. So you'd want to add your independent variable and your dependent variables into this template. So research hypothesis colon, the mean of sample 1 is significantly different from the mean of sample 2. Or another template that you could use is research hypothesis colon, there is a significant difference in the mean blank of whatever the dependent variable is between group 1 and group 2. So if we wanted to see what this would look like if we inserted the specific characteristics of our study into the template, it might be research hypothesis. There's a significant difference in the mean number of dates that cat people got asked on in comparison to dog people last month. All right, so we can also write our null hypotheses and symbols. So we first start off by identifying our null hypothesis using the symbol for null hypothesis, which is capital H sub 0. Then we put a colon to let people know that our null hypothesis is coming. Remember, we want to keep our groups in the same order. So we had group 1 first with our research hypothesis. We'll want to do the same thing with the null. So we have X bar sub 1. We know that our null hypothesis is the complete opposite of our research hypothesis. So we put the equal symbol. And then we'll write the symbol for the mean of group 2, which is X bar sub 2. And when we put it all together, we can see below that our null hypothesis in symbols is H sub 0 colon X bar sub 1 equals X bar sub 2. And then so we have a template for putting this into words as well. So we would write null hypothesis. The mean of sample 1 is not significantly different from the mean of sample 2. Or we could say null hypothesis, there's not a significant difference in the mean, and then you insert whatever your dependent variable is between group 1 and group 2. So if we wanted to use a real life example, we would say if we continue our last example that we were using, the null hypothesis for that other research hypothesis would be there's not a significant difference in the mean number of dates that cat people got asked on in comparison to dog people last month. So if you want to write your hypotheses non-directionally, we have the directions for that already. However, if you want to write your hypotheses directionally, which is actually the better thing to do if you can, if you have an idea of which group should be larger, or depending on what you're studying, if you have an idea what group should be smaller on the dependent variable, you actually want to write your hypotheses directionally. Okay, so if we do that, it's a very similar process, but instead we're going to identify which group we think is going to either be bigger or smaller. So in this circumstance, if we have an idea that we think that group 1 is going to be significantly larger than group 2, this is how we would do that. We would write H sub 1 to represent that we're writing a research hypothesis. Then we're going to put a a colon to say, hey, a research hypothesis is coming. After that, we're going to put X bar sub 1 to represent group 1's mean. Then we're going to put the greater than symbol if we think group 1's mean is going to be significantly larger than group 2. And then we'll finish it up by writing X bar sub 2, which represents the mean of group 2. And so at the bottom of this slide, you can see that we have H sub 1 colon X bar sub 1 is greater than X bar sub 2. So we can translate these symbols into words, and I have a template for you. So if we want to write this out in words, we'd write out the words research hypothesis, put that colon, and then the mean of sample 1 is significantly greater than the mean of sample 2. Again, you still have to insert the different variables from your study, but this is the basic format that you would use. You would just make it fit what study you're doing. So for example, research hypothesis, people who identify as women own significantly more pairs of shoes than people who identify as men. So if you wanted to test stereotypes about shoe purchases, you could do that. You could test that. So then we can also write our null hypotheses in symbols. It's pretty straightforward. So if we remember in our other example, we hypothesized with our research hypothesis that the group 1 mean would be significantly larger than the mean of group 2. So if we're writing the null hypothesis that goes with that other research hypothesis that we already did, this null hypothesis needs to cover everything that our research hypothesis doesn't. So we first start out by writing H sub 0 to identify that we're doing the null hypothesis. Then we'll put a colon to let people know that this is what our null hypothesis is. Remember, we're going to keep our groups in the same order. This is really important, especially when writing our directional hypotheses. Okay, so we'll put X bar sub 1. And then because this needs to cover everything our research hypothesis didn't cover, then we'd put the less than or equal to symbol. And then we finish it up by putting the symbol for the mean of group 2, which is X bar sub 2. And we can also have a template to translate the null hypothesis that was written in symbols into words. And here I have the null hypothesis template. So you'd write null hypothesis, you'd put a colon, the mean of sample 1 is less than or equal to the mean of sample 2. And it's really important. You will really want to save these PowerPoints and these slides, not just for this class. They're really handy, especially while working through different assignments for the class. But you may be in a situation later on where you don't have another statistics class, but you're expected to do research. And it's really helpful to have these templates where you could go back and reference for how you would write your research or null hypothesis. All right, so if we take our null hypothesis template and we plug in words, if we're extending the example that we did, null hypothesis, colon, people who identify as women own less than or equal pairs of shoes than people who identify as men. Step 3, then we want to check our assumptions. We remember that every analysis doesn't necessarily have the same exact assumptions. There's some assumptions that we'll see very frequently, but you'll want to make sure that you're checking the assumptions for the very specific analysis that you're doing. So with the independent samples t-test, we have very specific ones. We want our dependent variable to be measured on a scale. We want something called independence of observations. We want our dependent variable free of outliers. We want the population we took our sample from to be normally distributed. We want the variances of each population to be equal. This is going to be a new one. They call that one also homogeneity of variances. We want the sample to be randomly selected from our population of interest. So now we'll go through each of these assumptions and review how to test for them. So assumption, our dependent variable is measured on a scale. How do we do that? We know how to do this one already. How do we check this? This means that our dependent variable is on an interval or ratio level of measurement. So you meet this assumption if your dependent variable is on an interval or ratio level of measurement. You violate this assumption if it's on a nominal or ordinal level of measurement. So the independent samples t-test is not robust to the violation of this assumption. What this means is that if our dependent variable is not on an interval or ratio level of measurement, then we can't do it. Okay, so if our DV is not scale, you cannot do this analysis. You have to figure out what the non-parametric equivalent of this analysis is. This is because the mean is in this formula for the test statistic, and that's literally what we're comparing. We know that from our second chapter that if we cannot calculate the mean with data that's on a nominal or ordinal level of measurement. And so this is a deal breaker because it's literally in the formula. So if the dependent variable is on an ordinal level of measurement, you can actually look at the non-parametric equivalent called the Mann-Whitney test to see if you meet the assumptions for that analysis. Okay, so assumption independence of observations. This basically just requires that the participants don't influence one another's results. Okay, so one way that we check this is that our two groups are actually mutually exclusive, right? With this means that we use a between group design. So as long as we don't believe, if we have no reason to believe that one group is influencing the other group, then just by the nature of using between group design, we believe that we meet this assumption. However, there may be a situation. So a long time ago, I wanted to compare the learning of my in-person statistics class to my online statistics class to see if there are significant differences. And then this is before I made videos for my online stats class, but they asked, some of my online students asked if they could come to my in-person class. And so I allowed that to happen. And the moment I did that, I could no longer compare my two groups with one another because my groups were no longer mutually exclusive, because just by the nature of having those online students in my in-person class, the groups, it was no longer separate groups because they were influencing the makeup of the class. And then another way that we look for this is that all cases within each group are independent of one another. And we believe that we meet this assumption as long as we don't have any other reason to believe that someone was influencing someone else's score. So if I was giving a final exam in a class and one of my students shared their answers with everyone, those cases would no longer be independent. So independence means that they have to be able to provide their own data that's not influenced by someone else in the study. The independent samples t-test is not robust to violation of this assumption. If you violate this assumption, you cannot do this analysis. Okay, so again, if observations are not independent, you cannot do the independent samples t-test. Okay, another assumption is our dependent variable is free of outliers. How do we test for this? Because we've seen this one a few times now. So to test this assumption, we're going to find the z-scores of each individual x value or the data from our participants of our dependent variable. Okay, and we'll do this with relation to each of the groups. So that means if we're comparing two groups, for group one, we'll find the mean and the standard deviation so that we can find the z-scores of each individual x in that group. And then we'll have to do the same thing with group two. We'll have to find each z-score for each individual x value of that group. So that means for group two, we would also have to calculate group two's mean and then also the standard deviation of group two as well. So we remember that an outlier is defined as any score with a z-score at or beyond of plus or minus 3.29. So that means if you have a z-score that is positive 3.29 or bigger, or a negative 3.29 or smaller, those are outliers. If you have a dependent variable that has any outliers, you violate this assumption. However, the independent samples t-test is robust to the violation of this assumption if we remove the outlier prior to running the analysis. Note, if you remove any data points from your data set, you have to indicate that in the results section of your paper. You have to indicate how many participants you removed and why. So for this example, if you're using this way to identify your outliers, you would need to say, I removed however many because of the plus or minus 3.29 z-score criterion. Okay, then another assumption that we've seen is the population that we took our samples from were normally distributed. So although we don't have access to the population with this, we're talking about the populations that we took our sample from. We know we don't have access to that, but we do have access to our data set for our samples. So basically what we do is we test if our individual or two samples, if their distributions are normally distributed. And if they are, we assume that the sample or the population that we took those samples from are also normally distributed. So again, you're going to use the Shapiro-Wilk test for normality to test for this. If our Shapiro-Wilk test is statistically significant, which means our p-value is less than 0.05, then we violate this assumption. If our p-value is equal to or greater than 0.05, then we meet this assumption and we can move on. However, if we violate it, our independent samples t-test is robust to the violation of this assumption if our sample size is equal to or greater than 30. If not robust to the violation, so say like we have a smaller sample size than 30, you can check also to see if you can run a Mann-Whitney U test. So it has a few assumptions. It is the non-parametric equivalent of this test, but it's not the end all be all if you don't meet this and it's not robust. You can find a different analysis to see if you can run it. Okay, so here is our new assumption. This is homogeneity of variance assumption. What's the word homogeneous mean? It means the same. So here in this assumption, we're testing to see if the variances are approximately equal from our two groups. So you literally find the variance for group 1 and the variance for group 2, and it's comparing those two different ones. This assumption also relates back to overall populations, which we don't have. But we in this assumption would say that the variances are equal, but we do have access to our sample. Okay, so we test to see if there's basically significant differences between our two sample variances. And we don't want there to be significant differences. We want to have this homogeneity of variances. Okay, so we'll use something called the Levene's test. So here you want the p-value for the Levene's test to be greater than or equal to 0.05. So if your p-value for the Levene's test is equal to or greater than 0.05, you meet this assumption. And you violate the assumption if your p-value is less than 0.05. So this is something that I would just give you. There is a formula for the Levene's test, just like there is a formula for the Shapiro-Wilk test. But for this class, I will just give you the p-values and you'll have to determine if you meet the assumption or you violate it. If you violate the homogeneity of variances assumption, but you meet all of the other assumptions, you can use the unequal variances t-test to analyze the data set. All right, so SPSS is the software that we use to run statistical analyses. It can run the Levene's test. It can run the Shapiro-Wilk test for normality. There's other types of software out there. This one's one of the predominant statistical softwares that's used in psychological science, although there's tons of other ones that are gaining more popularity. This is just the one that I was most heavily trained on. So when you run an independent samples t-test in SPS software, it automatically tests the Levene's test for you. Okay, so you go to the output of the Levene's test for equality of variances, and then it will provide you a number under the SIG period column. That is your p-value. So all you have to do is look at that value. If it is 0.05 and bigger, you meet the assumption. If it is less than 0.05, then you violate the assumption. It's that easy. Okay, so what do we want our p-value to be to meet the assumption again? To meet the homogeneity of variance assumption, you want your p-value to be greater than or equal to 0.05. Okay, again, when the independent samples t-test is robust to the violation of the homogeneity of variance assumption. So if if it's the p-value is greater than or equal to 0.05, we meet the assumption, we're done. We can continue to check on in our other assumptions. However, if it's significant, we violate this assumption. But the independent samples t-test is robust to the violation of this assumption if the larger group variance is less than 2 more times than the larger times larger than the smaller group variance. That's really hard to say. Let me say that one more time. So if the larger group variance, so if you have the bigger variance, the group with the bigger variance is less than 2 times bigger than the smaller group variance, you can still do this anyway. You can still run this analysis. Okay, so let's write this out for you. So this means we can still do the analysis if we violate this assumption, if the following condition is true. So we see which group has the bigger variance, right? Because we know that S squared is our symbol for sample variance. So if we divide the larger variance by the smaller variance, and if that number is less than 2, you can still do this analysis anyway. Okay, so let's do some practice. So if you get this result from SPSS, do you meet or violate the homogeneity of variance assumption? You meet it. That's because that p-value, which is found under SIG period, is bigger than the alpha level of 0.05. This indicates there's no significant difference between the variances of each of the two groups. This means you have homogeneity of variances. Okay, so practice 2. If you get this result from SPSS, did you meet or violate the homogeneity of variance assumption? We failed to meet. In other words, we violated it. That's because our p-value is less than 0.05. So what would you need to do next? You need to check to see if the larger variance is 2 times bigger than the smaller variance. Okay. So if we continue this practice, how do we find the variance from this information that we have up in the right corner? So remember earlier from chapter 3 or week 3 that the standard deviation is the square root of the variance. If we flip that around, we know that to get the variance from standard deviation that we must square those standard deviation scores. Okay, so the relationship flips both ways. So variance equals our standard deviation squared. So if we go through and we figure that out, we see variance for that first group is 11.49. The variance for the second group is about 5.62. Okay, so to meet the conditions for it to be robust, the following condition needs to be true. Our bigger variance divided by our minimum variance is less than 2. So we would need to do that math. So we need to take 11.49 divided by 5.62. Go ahead and do that now. So would the independent samples t-test be robust to the violation of the homogeneity of variances assumption under these conditions? And here we see no, because the larger variance is more than 2 times greater than the smaller variance. So let's do that here. So I'm going to pull up my calculator. So 11.49 divided by 5.62. And that result was about 2.04. So that is more than, that means it's not less than 2 times greater than the smaller variance. So this means if you came into this situation, you need to use the unequal variances t-test. It has another name called Welch's t-test. They are the same thing. And then it brings us to our last, our last assumption. The sample was randomly selected from the population of interest. To meet this assumption, it just means that when you took your sample that you randomly selected it from whatever population you're wanting to study. Random selection means that every member of the population had an equal chance of being selected into the sample. So if you don't randomly select the sample, you violate the assumption. The independent sample's t-test is robust to the violation of this assumption if you don't generalize the results from your sample back to the population you're interested in studying. All you can do is talk about your results with what you found in your two samples. You also would need to write about this in the limitation section of the discussion section of your research manuscript. All right, so here I just have a couple tables for your notes that you can use while you're working through different problems with this. So here's the first four. We see what the assumptions are. And then we see if it has a role for being robust or not. And we have for the rest of the assumptions as well. So you don't necessarily have to write these all down. You will want to keep your notes again. You may want to print them out, but you also may want to put them into a Google Drive that's not associated with your UCM account, because that way you can have them later when you're off in grad school or in the real world if you ever need to run some of these statistics. Step 4, then we're going to calculate our test statistic. And you could just plug and chug this formula. We know what each of these symbols means. So we know X bar sub 1 minus X bar sub 2. So we're taking the mean of group 1 minus mean of group 2. We know that S squared stands for variance, and we see a sub 1. So we're saying the variance of group 1 times open parentheses, the sample size of group 1 minus 1, close parentheses, plus the variance of group 2 times open parentheses, sample size of group 2 minus 1, close parentheses, all that divided by degrees of freedom, which we will learn how to calculate degrees of freedom. That's going to be a new one. And then we multiply that by 1 divided by the sample size of group 1 plus 1 divided by the sample size of group 2. So we're going to learn about degrees of freedom now. Its symbol is DF, so you're going to want to put that onto your symbol sheet right now. You're also going to want to put the symbol for our t-test as lowercase italicized t. So that is our t-test statistic is symbolized by t. Our degrees of freedom, here's our formal definition, but we're going to talk about this a little bit, is the number of data points in a sample that are free to vary when estimating the population parameter from the sample. Okay, so I have a metaphor. I bet you are so shocked, but I have a metaphor for degrees of freedom. All right, so let's say we want to go on a 3-day weekend trip. We're very excited. Okay, say we want to stay Friday, Saturday, and Sunday night. And we only packed 3 outfits, right? So if we're staying Friday night, we have the outfit for Saturday, Sunday, and Monday. If we wanted to wear a clean outfit each day and our Airbnb doesn't have on-site laundry, Saturday morning, we have the choice of 3 different outfits we could wear. We have a choice still. Sunday morning, we have a choice of 2 outfits that we could wear. Then when we come to Monday, however, we have no more choice. If we want a clean outfit and we can't buy anything new and we can't wash it, we're going to wear our last remaining outfit. We no longer have any choice. Okay, so again, Monday morning, we no longer have the freedom to choose from different outfits. So in this situation, our degrees of freedom is 2. There are only 2 days that we have an opportunity to choose between different outfits for the day. Okay, so we can use the mean actually to teach about the degrees of freedom a little bit more. So here we see we have a data set where we have all of the X values except for 1. Okay, so if we're trying to use a sample to make guesses about a population parameter, so in this situation, we're using a sample to try to get to a population mean. If our sample size equals 5, and if we remember M equals mean, can be the mean of a sample or a population. If our mean is 5, our first 4 X values are free to vary. But once we get to that 5th X, it'll have to equal a very specific number. Okay. So how would we solve for that last remaining X value? So here thinking we actually have the formula for the mean, right? So what would we have to do? I want you to try to come up with the answer before moving on, so that this hits home. All right, so we have the formula, right? We have x bar equals the summation of x divided by the sample size. Here we have almost all of the information, right? We know that our x bar or our mean is 5. So we have 5 equals the summation of x. Now this is where it gets a little complicated because we have all of our x values except for 1. So what would we do for our numerator? If you said we would have 3 plus 6 plus 5 plus 4 plus x sub 5, you are correct. And then divided by our sample size, which we know is what? It's 5 because we have 5 participants. So when we do this, there's a couple ways you could do it, right? You could solve where you have 5 equals the summation of x divided by 5. And so we know that when we do that, to get the summation of x by itself, we'd have to multiply both sides by 5, which would eliminate the fraction on the right side of the equation. And then it would make our summation of x equal to 25. And if we did that, then we could subtract, or we know that our x sub 5 would be 25 minus 3 minus 6 minus 5 minus 4. Okay, so we find that it doesn't matter what those first 4 values of x are. They could be anything. And then if that's the case, then our last x doesn't have any choice. It doesn't get to be anything else. So in this circumstance, because the mean was 5, our 5th x had no other choice than to be 7. So there's a very specific way to calculate degrees of freedom for the independent samples t-test. And there's actually 2 different ways. So we have DF sub 1, which is the degrees of freedom for your first group. So that's the size of your first group minus 1. Then you can get your degrees of freedom for your second group, which is the sample or the size of your second sample minus 1. And then to get the degrees of freedom for the entire thing, you add those 2 different degrees of freedom together. Okay. Another way that, so if sometimes you'll see DF by itself, if you see DF by itself and there's no sub number or letter or anything, then that means degrees of freedom total. Another way that you could do it is do the total sample size, like of the entire study, and then minus 2. Or you could find the degrees of freedom for each of the individual groups and add them together. All right, so something that we need to learn about is called pool variance, okay? So if our sample sizes are different, that's going to make our formula a little bit more complicated. And so if we see here that if groups have different sample sizes, so if group 1 has like 10 participants and group 2 has 9 participants, you actually have to go in and do something called pool variance. But the formula is a little bit more difficult because you have to take in consideration which group had more participants in it so you can account for it. However, if you don't have a different number of participants in each group, you can actually just take the average of the 2 variances to find the pooled variance. So an example of this pooled variance relationship with sample sizes. So we see here in the middle of our number line that if our first group, right, has the same sample size as group 2, we look at the 2 different variances, right? So we see that on the far left that group 1 has a variance of 10. We see that group 2 has a variance of 15. If both of them have the same sample size, then we see that the pooled variance is going to be right in the middle. It's going to be the average of those 2 or the mean of those 2 variances. However, if we look at our other one that's a little bit lower on our slide here, and we see, let's say that group 1 had a sample size of 10 and group 2 has a sample size of 5, when we pull those together and use that other formula, we see that the pooled variance actually pulls toward the group that has larger sample size. Okay, so say we have two samples. When the sample sizes are equal for each group, the pooled variance is in the middle. If one group has a larger sample size, the pooled variance gets pulled toward the larger group. Okay, so if we actually look at this formula, if we go back to the other formula, what we're doing right now is actually breaking down that big scary formula. So we're taking this and we're going to simplify it using kind of that pooled variance. So I'm going to move this back really quickly back to where we were. And so what we're doing right now is trying to break down that big scary formula into a smaller one. All right, so we see here, you can actually simplify that big scary formula that we had to show that we're taking the difference between our two means and we're dividing it by the square root of that pooled variance and timesing it by 1 divided by the sample size of group 1 plus 1 divided by the sample size of group 2. So that denominator, so if we see here, that denominator actually has its own name, and that is called the standard error of the difference between means. Okay, so this is very kind of complicated, and honestly, I don't expect you to understand that, like, or remember even the intricate details of this, but this is going to lead us to an understanding a little bit more about what this formula is trying to do. So still stick with me, even though I don't plan on making you regurgitate all this information. It will help us understand what we're doing with the independent samples t-test. All right, so the standard error of the difference between means. This is the standard deviation of mean differences between samples if we found the differences between every potential sample of the same size from each of the populations. That is a really big definition. The biggest thing that I want you to take from this, it's basically a type of standard deviation. Okay, and we're going to take that back and look at our formula. All right. So if we're looking at this, if that standard error of the difference between means is basically a type of standard deviation, this t-test statistic is essentially giving us what information? It's type of what? It's almost a type of z-score, right? Because if we look, we're seeing, okay, how big is the difference between these two groups, right? And then we're saying, okay, so we're dividing that difference between our two groups and dividing it by what we see as kind of the typical variation that we would have between these two different groups. And we're using that as a threshold so that we can have our t-test statistic is just telling us, it's quantifying how big those differences between our two groups are. All right. Step 5, then we're going to find the critical value or values. You're going to use student T's distribution table, which is in our module materials for this week. Another way this is called, it's sometimes called the T critical value table. It is different than the area under the curve table. So when you print this off to be able to use, you're going to want to label it that it's the T critical value table. Okay, so to do this, you have to figure out which alpha level you're going to use. Here we usually use 0.05 unless I tell you otherwise. You have to use those degrees of freedom that you calculated. And then you have to determine whether you're using one-tailed or two-tailed test so that you can find these critical values. How do we determine if we're doing a one-tailed or a two-tailed test? It goes back into how we wrote our hypotheses. If we wrote our hypotheses directionally, we're running a one-tailed test. If we wrote our hypotheses non-directionally, we're doing a two-tailed test, okay? All right, so degrees of freedom, DF. Again, this is the number of data points in the sample that are free to vary when estimating the population parameter from that sample. We went through these already. The other way is just take the entire sample size of both groups combined and -2. It's the same thing. Steps of finding your critical value for T using the student T's distribution table. First, you have to determine the alpha level. So we know that the two most common alpha levels are 0.05 or 0.01. And then you're going to locate the correct alpha level in the T critical value table. You're going to determine if you used a one-tailed or two-tailed test and locate that column in the table. You're going to find the row that corresponds with the degrees of freedom for your data set. And you're going to intersect the column with a proper alpha level and number of tails in the test with the degrees of freedom to find the critical value of t. So this is what it looks like. So again, you're going to look and say, which alpha level did you use? In this case, we use 0.05. You got to determine, did you write your hypotheses directionally or non-directionally? So if you wrote them directionally, you're going to look at this one-tailed column. Then you're going to find what the degrees of freedom for your data set, let's say it's 10. And then you're going to intersect the columns, and we'd see that if we use alpha level of 0.05 for a one-tailed test with the degrees of freedom of 10, our critical value would be 1.812. Step 6, then we're going to make a decision. To do that, we're first going to label our normal curve. Then we're going to write our decision out in words. Then we'll write our decision out in symbols. So labeling our normal curve for a two-tailed test, which means that we wrote our hypotheses non-directionally. We see that we have two critical values. One will be positive, the other will be negative, but the number will be the same. We have to label the retain the null hypothesis region and the reject the null hypothesis regions. If we wrote non-directional hypotheses, we'll have two different regions that are reject the null hypothesis. And that's because when we did the non-directional hypothesis, we didn't have an idea which group would be bigger, right? So we're looking on both sides of it to see if that difference fell in favor of either of the groups. Labeling the normal curve for a one-tailed test where we have a positive critical value. Where do we determine if we have a positive or negative critical value again? If you said, look at the research hypothesis, you're correct. All right. So here we see that if we said in our research hypothesis that one group was significantly greater than another group, we have a positive critical value, which puts it on the right of 0. We only have 1. We know that our critical value separates us between the two decisions that we can make, whether we retain the null hypothesis or we reject the null hypothesis. This is what it would look like to label a normal curve for one-tailed test with a negative critical value. We would have it on the left side or tail on the left side because we know to the left of 0s are negative numbers. We would have the retain the null hypothesis region, our critical value, and our reject the null hypothesis region. So if we did this, because when we're labeling our normal curve to make a decision, we know that we also have to label the test statistic that we calculated earlier on using our formula. So if we had a t-test statistic equal to -3, what decision would we make? If that was our critical value of -1.812, we went beyond that number, and we know that we would reject the null hypothesis. Okay, what decision would you make with this one? So here we see we ran a two-tailed test, which means we had non-directional hypotheses. And we have both of our critical values labeled, one positive, one negative. They're the same number. And then we plotted our t-test statistic on the number line underneath our normal curve. And we see that we will make which decision. In this circumstance, we would retain the null hypothesis because our test statistic did not move beyond our critical values. Okay, so there's different ways that we can write the results in symbols for non-significant or for whether we have non-significant results or significant results. So when we retain our null hypothesis, another way to say that is that we found non-significant results, which means our differences weren't big enough that we're not sure those differences occurred to anything other than chance, right? So when we do this, it's a little bit different. It's still going to follow the same format that we learned for the one sample Z test, but we're going to see a few differences. So first, you have to identify the test statistic used to analyze the data set. So for the independent samples t-test, the test statistic is t. So here we'll put the lowercase italicized t. Hopefully that is on your symbol sheet already. After that, we'll have an open parentheses, and then we'll put the total degrees of freedom, close parentheses, equals. Then we put that test statistic value that we calculated using our formula in step 4. we'll put a comma, then we'll put P, which represents p-value. We don't actually calculate the p-value for this because we use our test statistics and we're comparing that to our critical values. But we'll put our p-value equals n dot s dot. So when we have non-significant results or insignificant results, that means our p-value is greater than or equal to our alpha level. And when this happens, we just write n dot s dot, which stands for not significant. So then after that, we would write our results for significant results, but I'm going to show that after we do step 7, because if we have non-significant results, we're done. We don't have to do anything else. If we have significant results in step 6, where we rejected that null hypothesis, then we're going to move on to step 7, which is conduct relevant follow-up analyses. So for the independent samples t-test, there's a few different follow-up analyses that we could do. We have Cohen's d and R-squared, which are types of effect size. And we can also calculate confidence intervals as well. So effect size. Effect sizes explain how much two sample distributions overlap with one another to help determine how meaningful the difference between our samples is. So when we reject our null hypothesis in step 6, that doesn't tell us how big the differences are. All it tells us is that there's enough of a difference between the two groups that we don't think it occurred due to chance. Okay. And so for the independent samples t-test, there's 2 ways to do this. There's Cohen's d, which is symbolized by lowercase italicized d. That should go on to your symbol sheet. And then we also have R-squared, which symbol is very intuitive, and it's just R-squared. So for Cohen's d, here what we do is we have a formula where we have the mean of the first group minus the mean of the second group, and divided by the pooled standard deviation. Okay, so we take the difference between the sample means and divide that by the pooled standard deviation. And if you see this really cool visual here, this kind of gives us an idea. So like whenever we have, sorry, it's not, because I'm using Zoom to record this video, it's not letting me see everything that I need to see. So I'm going to pause this real quick. So in this table, I actually give you the interpretation guidelines. So we see that when we have a Cohen's d of 0.20, that means it's a small effect size. And if you look at the visualization there, you can see that if we were to plot both of the distributions for each of our samples, that most of it overlaps. As we get bigger and bigger effect sizes, we see that there's not as much overlap between the two different group distributions. So medium effect size, once you get to 0.50, it's considered a medium effect size for this. And then once you get to 0.80, it becomes a large effect size. Then we also have R-squared. The formula for this is R-squared equals t-squared. So that t is that test statistic value that you calculated in step 4, divided by t-squared plus the degrees of freedom. And this effect size tells us the proportion of the variability and the participant scores that is attributed to the group membership. There is another type of follow-up analysis, and this is kind of a newer one for this, called confidence intervals. And this actually provides a range of values that likely contain our population parameter. So we know that in all of our obtained scores, there's always a likelihood for error in it, whether it's because we took a sample, because we measured it, or because it was just random error that occurred. And so what we do with the confidence interval, it actually provides us a range of values that actually contain probably that population parameter within it. Our symbol for confidence intervals is going to be capital C, capital I. Make sure to go ahead and put that onto your handy dandy symbol sheet. Our formula for this is a little wild. Okay, so if you're doing a 95% confidence interval, you would write 95% CI, which represents confidence interval, sub LL. The LL stands for lower limit of your confidence interval because we're going to have a range. And then you fill in the rest of this formula. A lot of these things are things that you already found. However, if you did a one-tailed test, you're actually going to have to find the critical value that's associated with the two-tailed test to be able to establish a confidence interval that spans both sides. And so you'll see it's basically the same formula, except for the lower limit, you're subtracting, and then for the upper limit, you're adding. Okay, so steps to determining the critical value associated with your desired confidence interval. First, you got to determine the type of confidence interval you're wanting to do. Are you wanting to do a 95% confidence interval or a 99% confidence interval? You're going to convert these into convert the percentage into a proportion. So if you're doing 95%, you're going to convert that to the proportion 0.95. You're going to take 1 minus that proportion to identify the alpha level. So in this case, if we wanted a 95% confidence interval, we'd take 1 minus 0.95. Then we'll use the t-critical value table to find the critical value for a two-tailed test for this alpha level and the degrees of freedom from your sample. So when we write our significant results, people actually suggest that when you're doing an independent samples t-test, that you include both the effect size, one of the effect sizes, and the confidence interval as well. We won't get into this much for this class, but you could actually use confidence intervals to do significance testing like we're doing, the way that we're doing with our test statistics and our critical values. It provides different information, so it's actually good to do both if you can. So when we're writing our significant results here, we see the first thing that we're doing is we have our T, which is the test statistic that we're doing. Don't get confused. T doesn't equal test statistic. T is a type of test statistic. So right now, like if we think about our one sample Z test, our test statistic for that was Z. For the independent samples t-test and our dependent samples t-test that we'll learn next, our test statistic is T. When we move on to learn about ANOVAs, the test statistic will be F, and so forth. So you'll have your test statistic, and then you'll have open parentheses, you'll put your degrees of freedom. And close parentheses, you'll put equal. So then you put your test statistic value that you calculated with the formula. If you had significant results, then you're going to have a comma that your p-value is less than your alpha level, which is 0.05. Then when you calculated your Cohen's d, we found like you put whatever that value is from that formula. So let's pretend it was 1.46. Then you put a comma. Then you'll put R squared, which represents the effect size of R squared, equals whatever you calculated with that formula. Then put a comma. Then you'll put your confidence interval information, which is we did a 95% confidence interval. Open bracket, 0.01, which is the lower limit of our confidence interval, comma, 37.19, which is the upper limit of our confidence interval. So that is all for this week. We're moving right along. This will get easier as we move through more analyses and we get used to keep going through these steps over and over again. I am giving you quite a bit of information, but hopefully it'll get easier the more times we do it. Let me know if you have any questions. It's been really great getting to know a lot of you in office hours, so make sure that you're using them. We are moving into kind of the latter portion of the semester, so lots of more students are coming, but it's okay. My office is equipped to handle multiple students at one time. In fact, today I had a couple people on Google Meet from our class. So if you need to use them, we can either figure out using a Google Meet or you can come in person, but definitely take advantage of it. All right, I hope you all have a great week.